In this video we are going to work out how to write electron configurations for few atoms. Now this is from the textbook I got. So you can see on the left hand side, here all the elements, the hydrogen, and on the right hand side I got periodic table. You have to understand something more about periodic table. Okay, you know the periodic table already, but at A levels you have to know something more than that. So in any periodic table you'll have the period. The horizontal lines are called period. You got period 1, you got period 2, you got period 3, period 4, period 5, period 6, period 7. And the vertical lines from the top, this is group 1, and this is group 2. And in a GCSE level, these are called the transition elements. Okay, they're not shown in a group. The group 3 starts here, in the basic periodic table. So this is your group 3, and this becomes the group 4. Somebody asks you what's the group of carbon, you will say that it is in group 4, and nitrogen in group 5. This is group 6, this is group 7, and the last is group 8. Group 8, these are also called as the noble elements. They are very, very stable. They don't want to react. So, but at A level, the group number starts from 1, 2. So they'll also continue from 3, 4, 5, 6. 3 will correspond to this thing, SC, and the 4 will go here. And your boron will have a group number 13. So this is like a advanced level of understanding the periodic table. It's very easy. Just take out whatever group number you see here. Take out 10 out of that. So you'll have a 3. So the group number 3 is boron. It's very easy to remember. So assume that if somebody says group 17, so 17 take away 10, that is 7. So there's nothing but the group 7 in the whole periodic table. You take away 10 because there are 10 groups here which were in a part of the transition metal. Okay, usually most periodic table they keep them aside because you're going to learn the transition elements in detail in A level, because these are the one that gives a color, the color chemistry. They're also called color chemistry. All the color you see, red, green, blue, all the chemicals and color of your t-shirts, they're all made out of these transition metals. They're called color chemistry. Okay, so that's all you need to know so far. So now we'll start working out some problems. I can say if you're good in this, you can always get full marks. Okay. Take for example magnesium. So this is magnesium, which is in period 3 and group 2, and the atomic number of magnesium is 12. So 12. Okay, and here, so because it has 12 protons, it will have 12 electrons. Now see that it is 1s2, 2s2, 2p6 and 3s2. Now how is there any way you can remember to write these numbers? So you can just do like this. You got so first identify. Okay, so magnesium has got 12 electrons. Now you have to distribute these 12 electrons. So you know that you got the shell. This is the first shell, second shell, third shell and fourth shell. First shell has got 1s, second shell has got 2s, it has got 2p. Third shell has got 3s, 3p and 3d, and fourth one has got 4s, 4p, 4d and so on. And always remember 4s will fill first. So this is something like 4s is in between 3p and 3d. Now you also know that S subshell can have maximum of 2. Now you want to distribute number 12, so take away the 2. So I'm going to give 2 will go here. Always, okay, the electrons filled from the closest shell and goes outwards. 2 here, I can give 2 there, so 4 isn't taken out. If you take 4, you got 8 is the remaining. So P shell, you can have maximum 6 in P shell. Now got 2 remaining. Now 2 will go to this one, 2s2. Okay, so you can see that you got 1s2, 2s2, 2p6 and 3s2. Now just couple of words you have to use here. See, the first shell can have a maximum of 2. The second shell can have a maximum of 8, and the third shell can have a maximum of 18. Okay, so this is what you know about the shells. And the fourth shell can have a maximum of 32. Now compare here. In case of magnesium, the first shell has got 2. You can say that the first shell is full. You can use this word called full. If the shell is full, there is no any free space to accommodate any additional electrons. It's full. What about the shell number 2, the second shell? The second shell can have a maximum of 8. In magnesium, the 8 electrons are already there. You can also say that the second shell is full. The third shell can take a maximum of 18 electrons, but only 2 are present in the third shell. You can say that this is partially full. Okay, so in other words, the third shell has got some space to accommodate more electrons. Okay, you should use this word full shell, and partially full. Okay, take one more example now. Now we'll do it for nickel. So nickel is Ni. Okay, this is the one. Okay, this is the one, nickel. So in the periodic table, nickel is over there. So the atomic number is 28. So it has got 28 electrons. We have to distribute these 28 electrons now. So start from here. Okay, N is equal to 1, 2, 3, 4. Now first shell can have a maximum of 2. Second can have 8. This can have 18. And this can have 32. Okay, now so in the first shell you got only S. So you can start writing like this way. So 1s. Second one you got 2s, you got 2p. Third you got 3s, 3p and 3p and 3d. And fourth you got 4s, 4p, 4d and 4f. Okay, and also keep in mind S can have maximum 2, P can have maximum 6 and D can have maximum 10 and F can have maximum 14. These are the background you have to know. Okay, I'll start giving the electrons now. 28 electrons. So the first shell is full. See the word I've used, the full. First shell is full. Second shell 2 goes there and 6 goes here. So second shell also full. Third shell, okay. How many were given altogether? 2 and 8 here. So already now out of 28, 10 is gone now. You got 18 more. So the 3s will take 2, 3p will take 6. Now keep in mind 4s is the one that fills next. After this you have to fill 4s. You know the 4s orbitals are closer to the nucleus than 3d orbitals. Okay, use this way. Use this type of sentences. 4s is closer to the nucleus than 3d. So it is the one that's going to fill first. So S, so it doesn't matter. It takes maximum 2. Okay. So how many you got now? Out of 18, you got 8 and 2. Okay. 10 you are given. So you got remaining 8. Okay, 8. Now 8, see the d orbital can take 10 maximum, so 8 will go there. So once you do this, your answer should be like this: 1s2, 2s2, 2p6, 3s2, 3p6, and here you can either write in a 3d8 and 4s2. You can do like this way, or in some books, and what they do is they first write 4s2 because this is the one that got filled first, then 3d8. Okay, either way, it is fine. Okay, you can either write this, you can stick with this way. Okay, so what you got is compare with the result. So we got exactly the same result. Okay, so we'll do one more example, this time for krypton, Kr. So we already know it has got the atomic number is 36, and in the periodic table krypton is here, and you have to speak, use some proper words here. Krypton is in period 4 and group number 8. Okay, now so krypton Kr is 36. Okay, you can, if you once you're used to this, you can just start say 1s2, okay, 2s2, 2p6, that's fine, 3s2, 3p6, and 3d, that before 3d you got 4s there as well. Okay, so write 4s, 4p, 4d, and 4f. Okay, so how many you got? So for 2, 8, you got 2 plus 8 plus 8. Okay, so totally 18 have been distributed. Okay, now you got 18 more, so 18 more. So next is, so 2 will go here because it's a 4s shell. Okay, so if you take 2, you got 16 more. Okay, now next orbital to fill is 3d. D orbital can take 10 electrons, so it can give maximum 10 will go there, so you left with the 6. Okay, so remaining 6, that next is p orbital, so p can take 6, that this is the one. Okay, so check that whether answer is right. If you look at this, this answer is okay. 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6. Okay, so after that, don't keep the answer like this way, because they expect you to write like this: 2s2, 2p6, 3s2, 3p6, then 3d10, then afterwards 4s2 and 4p6. Okay, so next you have to understand what is the shortcut way of writing electron configuration. They might ask this in an exam. So it's basically about, is there any way you can reduce, okay, the length of the configuration. So sometimes the configuration can become very, very long. So to understand this concept, you have to know about this, the group 8 elements. See, this is the group 8. So group 8 elements are also called noble gases. Noble gas. They're called noble gas. They're called noble because they don't want to interact with others. They are very, very stable. They're less reactive. Use this word called less reactive. They don't want to react. That's why it's noble. They're stable. So stable means, they've got a complete outer shell. I'm using this word called outer shell. Okay, the outer shell. Okay, it's complete. It's full. They don't have any free space to accommodate any electrons. In any chemical reaction, there's always a transfer of electrons. That's what the chemical reaction is all about. So there's something happening with the electrons. In a nuclear reaction, there's something happening within the nucleus. So the two things. Okay, we don't say chemistry. When you speak about the nucleus of an atom, you don't say it's part of the chemistry. No, it's part of the physics. Well, physics is all about studying what's inside the nucleus. Chemistry is all about studying what is outside the nucleus, how they interact. Okay, now they are called gas because in the room temperature, all these elements are in the gaseous state. Like say carbon, for example, at room temperature, it's a carbon, it's a solid, a charcoal or coal. But in the same room temperature, say 18 degrees centigrade room temperature, all these elements are already in the form of a gas. That's why they're called noble gas. So when you speak about shortcut notation, you have to know that you will be using this the last elements of every period. See the word here. See the way I speak here. in every period, say period number 1, the last element is helium. In period 2, the last element is neon. In period 3, the last element is argon. In period 4, the last element is krypton. In period 5, the last element is xenon. And in period 6, the last element is radon. Okay, something like that. Okay. So these are the more stable atoms. So we'll be using this a lot when you speak about the shortcut notation. And also just go through this periodic table, just go through that, some of the important, the basic information about what you see in a periodic table. See, when I move from left to right, okay, the number of electron increases by 1. Say helium, say hydrogen is 1. Next is helium. So you go like this way. Helium, it is 2. So you got 1 and 2. Then after that, start with next period, the period number 2. Lithium has got 3 electrons. Then comes beryllium, has got 4 electrons. And continue with the boron, 5 electrons, 6 electrons, 7 electrons, 8, 9, 10. After that, go to period 3, 11 electrons, 12 electrons. Okay. So the number of electron increases when you move from left to right. Okay. Now this concept is used to write the shortcut notation. Okay. So now we will try to use the shortcut notation. Look at this, hydrogen is 1s1. Okay, so hydrogen is 1s1, helium is 1s2. Now the next is the lithium. Now lithium, I can write this as 1s2 and 2s1. Okay, I can write 1s2 and 2s1. But see, what is this 1s1? What is this? I know that 1s1 is the electron configuration of the helium. Remember, helium is the end of the period 1. Remember, these two elements are in period 1 and this is the starting of the period 2. Now what we can do is, instead of writing 1s2 and 2s1, I know that 1s2 is the electron configuration of helium, so I can put a bracket here, say that helium followed by 2s1. Okay, just write the one that is extra in lithium. Lithium has got one more electrons than helium. So this is the shortcut. I can apply the same thing for beryllium. So beryllium, take the beryllium here. It has got 1s2 and 2s2. Now in the periodic table, if you look at the periodic table here, what the theory says is, whenever you come across element, go to the previous noble gas. You're in period 2, the previous will be period 1, so noble gas is helium. So I can use this the previous noble gas symbol in my electron configuration. So that is what the shortcut means. Oh, come on. Okay. Okay. Yeah. So go with the beryllium. Okay. So beryllium again, you got 1s2, 2s2 and 2p1, and the previous noble gas for beryllium is the helium again. This is the one. Okay, because when you work in period 2, you have to consider the noble gas in the period 1, that's He. Now He followed by all the remaining one, 2s2 and 2p1. Okay, there's no much difference when you use a shortcut for period 2, because the only advantage here is instead of writing 1s2 you will have He. But I'm not sure whether you're allowed to do like this way. Say for example, for the same beryllium, can I put beryllium is one after the lithium, isn't it? So can I put I think it will be confusing now. Okay, I don't think it's possible. So can I do like this way? Li and 2s, no, I don't this work. Okay, so always stick with the, I think the rule says you have to go with the previous noble gas element. Now the next thing is, the next noble gas is neon. Okay, so you'll be using this neon noble gas in your electron configuration when you start writing the configuration for period 3. Okay, take for example the period 3 sodium. Okay, sodium is the first in period 3, which is 1s2, 2s2 and 2p6 and 3s1. Look at the neon. So neon is 1s2, 2s2, 2p6. Okay, now this whole thing, this is the electronic configuration of a neon. So I can put in a square bracket Ne followed by whatever is extra 3s1. That's it, easy. Do the same thing for magnesium. Okay, again the first up to here is a neon. The only thing it has got is neon has got 2 electrons more than, sorry, Mg, the magnesium has got 2 electrons more than neon. So I can put the configuration of neon in a square bracket followed by 3s2. Simple. Go with the aluminium. So aluminium, everything up to here is same as a neon. So put this symbol neon followed by all the rest for aluminium. It's 3s2 and 3p1. Okay, so it's easy now. So try one more. So what about calcium? So calcium, no, not argon. Okay, yeah, argon is there. Go with the, say, chlorine. Okay, chlorine. Again, up to here it is a neon. So this matches here, this bit matches here. So I can use neon as a base, put a square bracket, and all the extra bits for chlorine. Chlorine has got 7 more electrons than neon. Okay, if you see that 3s2 and 3p5, a simple question: how many electrons chlorine has got, more has got compared to neon? So the number of electrons is what you see on the top. So chlorine has got 7 more electrons compared to neon. Okay, now, so understood. Now take one more example of so now we'll consider one in the period 4. In period 4, this is the period 4. So you have to consider the noble gas in period 3, that's argon. Okay, so argon, this is the electron configuration of argon: 1s2, 2s2, 2p6, 3s2, 3p6. Okay, now for next is the potassium K. So this is 1s2. Look at that, 1s2. This is 2s2, 2p6, then 3s2 and 3p6 and 4s1. Okay, so the nearest, I would say the nearest or the previous, okay, the previous noble gas is argon, which is up to 3p6. So up to here, this is the argon. So the electronic configuration of potassium can be written either in this way, the full form, or you can take argon as a base, then the extra 4s1. This also give you some more information. You can say that potassium has got 1 more electron than argon. So likewise, to write calcium, you can take argon as a base followed by whatever is extra. So calcium has got 2 more electrons compared to argon. Same thing here. You can, up to here, this will be argon, Ar. After that you got 3d1 and 4s2. Okay, so it has got 3 more electrons than argon. Okay, so that's it. This is what you have to know. This is what the shortcut means.